Hey, Honors Chem, here's another video to help you with answering the questions from Chapter 9, Lesson 9, Chapter 9, your weekly work. This particular lesson is going to focus on mass calculations for reactions, or what we like to call mass problems. Just as a reminder, we're in Lesson 9, Chapter 9 of our textbooks, Section 9.3, and this particular tutorial, this particular video is going to cover pages 255 to 258. The section is entitled Mass Calculations for Reactions. We're basically going to combine a lot of previous concepts, a lot of previous things that we've been doing in chemistry. We're going to be using molar mass, which we need for this section, we need the periodic table. We're going to be using, from my previous video, mole to mole ratios. So in addition to needing a periodic table, you're also going to need a balanced chemical reaction. In this particular problem, it's sample problem 9.4 on page 255. We're going to be jumping from grams of substance A, whatever that substance is, and we'll talk about how the questions are worded, to grams of substance B. Keep that in mind. We're going to go from grams of A to grams of B. We cannot directly compare grams of one chemical to grams of another chemical because they don't have the same molar mass. We know that different chemicals don't weigh the same. So in order to go from grams of A to grams of B, we need to go through moles, and that's what we're going to do. So we're basically going to combine some calculations that we've already been doing. Here is the sample problem 9.4 on page 255. I am going to read it just so you have an idea of how this applies to real life. If you give me 1 second here. In the engines of cars and trucks, nitrogen gas and oxygen gas from the air react at high temperatures to produce nitrogen oxide or nitrogen monoxide, a component of smog. We've all heard of smog. This is what pollutes the air from car engines. Complete the following to help answer the question. How many grams of nitrogen oxide, here's the question, how many grams of NO? I want to stop there. Our answer is going to be in grams of NO. We want grams of this. But how many grams of that can be produced when 12.5 grams of O2 reacts? Our initial measurement, what we're going to start with, is 12.5 grams of oxygen gas. We are going to essentially jump from grams of O2 to grams of NO. I want to reiterate right now, or I want to make sure you all are aware, this question, the way it's worded, has nothing to do with nitrogen gas. We're going to assume that there's plenty of nitrogen gas in the air, and there is. We have more than enough of what we need, so we're not worried about this chemical at all. We're simply going to jump from 12.5 grams of O2 to grams of NO, using the molar masses of each of these two chemicals, as well as the mole-to-mole ratio. I guess I want to talk about the mole-to-mole ratio first. Even though we are not talking about nitrogen gas in this case, what is the ratio? I've been doing this in a lot of videos. Hopefully you understand what the mole-to-mole ratio is in this balanced equation. The mole-to-mole ratio is a 1 to 1 to 2. We're using the coefficients in front, not the subscripts. So if we were talking about the mole-to-mole ratio of oxygen gas to nitrogen oxide, the ratio would be a 1 to 2. We're going to use that. Now I'm going to move the screen down because this is, like I said, it's going to combine a lot of different calculations, and I'm left-handed, so I'm going to do the best I can. But we're going to be able to go from grams of chemical A, we'll get that into moles, then we'll do the mole-to-mole ratio, then lastly we'll go from moles, we'll find the molar mass of chemical B, and we'll find the number of grams. Again, I don't want to go too fast. If we react 12.5 grams of oxygen with plenty of nitrogen, how many grams of nitrogen oxide, how many grams of this stuff could we make when we react 12.5 grams of oxygen? Let's find out. We're going to start with our initial measurement. 12. Oh, I'm probably going to run out of room, but I'm going to do the best I can. And I'm sorry if it's messy, but I want this to help. 12.5, well, it's supposed to be a 2. 12.5 grams of O2. We're going to start with that. That's our initial measurement. Put that over 1. We need to go from grams of O2 to moles of O2. This is still our first chemical. So we're going to make another fraction. We're doing some dimensional analysis here. We bring down grams of O2, and we're going to find the molar mass of O2. Please keep in mind it is O2. For every 1 mole of O2, our periodic table tells us that, let's see if you can see that right there. Each oxygen is 16 grams right there, 16 grams per mole, but it's O2. So for every 1 mole of O2, it has a molar mass of 32 grams per mole. We need to keep going now. We're going to now jump, because grams of O2 cancels out. We're going to jump from grams of O2, excuse me, I'm sorry, from moles of O2 to moles of chemical B, nitrogen monoxide or nitrogen oxide, which is what they're asking us about. So right here, this third fraction in a mass-mass problem is the mole-to-mole ratio. So we're going to jump. We're going to go moles of O2 to moles of NO. And this, ladies and gentlemen, is where you use your coefficients. That's the mole-to-mole ratio. For every 1 mole of O2, we set that to 1 because there's no coefficient in front. That's a 1. There are 2 moles of NO. We're essentially multiplying by 2 in this section right here, because it's a 1-to-2 ratio, these two chemicals. So what does that do? That cancels out our moles of O2, and now if we answered the question, if we stopped right now, we would be in moles of NO. It doesn't want that. It wants grams of NO. So we're going to do almost the same thing we did here. We're just going to use the molar mass of NO, and instead of dividing by the molar mass, we're going to multiply. We're going to get this. That's supposed to be a multiplication symbol. We're going to go from moles of NO to grams of NO, and I am going to turn so I have enough room here, just barely enough room. Moles of NO on the bottom, 2 grams of NO. Here's a spot where a lot of students struggle. They see the 2 in front of the NO and think that a 2 needs to go here. Nope, that 2 has already been taken care of here in the mole-to-mole ratio. All we're doing right here is finding the molar mass of NO. The molar mass, 1 mole. So we're going to say for every 1 mole, you got to go back to the periodic table. You've got oxygen with 16 and nitrogen with 14.01. If you add those 2 up, not the 2, just the molar mass of the chemical, for every 1 mole of NO, there are 30.01 grams of NO. What does that do? That cancels out the moles, and we have successfully, we haven't answered it yet, but we will. We have successfully gone from grams of O2, using the molar mass, to moles of O2. Moles of O2 to moles of NO, using the mole-to-mole ratio. We jumped from chemical A to chemical B right here. And lastly, we're in chemical B. We went from moles back into grams using that chemical's mole-to-mole ratio. This is a mass to mass problem. Let's find out how many grams of NO can be produced from 12.5 grams of O2. Here we go. Get out of the way here. 12.5 is what I have, and I'm going to Ignore the ones because anything multiplied or divided by 1 is itself. So I'm using the Mr. Lambert shortcut here. If you want to multiply across the top, you can, and then you could divide by 32. I'm just going to go left to right, read it in chunks. 12.5 divided by 32 times 2, because that's in the numerator, times 30.01. 30.01, and we get right there. Bring that back. Keep in mind our initial answer has our initial measurement, excuse me, has 3 sig figs right here. So our final answer is going to be 23.4. 23.4 what? 23.4 grams of NO, our final answer. We just went from, I'll circle that, we just went from grams of a reactant to grams of a product. I'm going to do one more solution, one more sample problem with you, because it's important you understand if you get a different reaction, you can actually go from grams of a product to grams of reactant. It's just that the wording of the question is going to be a little bit different. Okay, so I didn't like a lot of the example problems that were in the book that dealt with grams of product going to grams of a particular reactant. So this is one that I made up, and we're going to answer it together. You can always refer back to these, but again, I wanted to show you how you can go from grams of a particular product, in this case there's only one, to grams of a particular reactant that you are asked about. You're not going to be asked about both in this case. Here is a balanced chemical equation. Nitrogen gas plus hydrogen gas yields NH3, which we call ammonia. It's the production of ammonia. The ratio, it is balanced. The ratio is a 1 to 3 to 2 in this particular case. Here's the question. We're going to do a grams to grams jump. How many grams of H2? So our answer is going to be in H2. How many grams of H2 or hydrogen are required? How many grams are required? It's a reactant, so we need some, right? How many grams of that are required to produce 43.2 grams of NH3? So what the question is saying, it's asking, we are going to produce 43.2 grams of this stuff. We want to know how much of this stuff we need. This is why I find this stuff incredibly important. You think about chemical manufacturers, business manufacturers, they're trying to make the most product possible with the least amount of waste. So if I'm trying to make a bunch of ammonia, and I know how much ammonia I'm trying to make, I had better know how many grams of reactants I need so that I don't have a lot of stuff left over. The question is not asking anything about nitrogen. You can ignore it for now. We're going to do a jump from grams of NH3 to grams of H2 using our periodic table with the molar masses as well as the mole-to-mole ratio. Here we go. I'll make this quick so the video isn't too long. We have 43.2 grams of NH3. It's always important to label. Sorry for the messiness. I'm trying to do this so you can all see it. We're going to bring down grams of NH3, and we're going to go to moles of NH3. We're going to use the molar mass, moles of NH3. For every 1 mole of NH3, we can look that up on Google. I'm going to do that right now. I think I know what it is in my head, but I want to double check. Yeah, I did have that had that in my head. 17.04 grams per mole. We can cancel out the grams. We now have moles of NH3. The next fraction is going to be our mole-to-mole ratio. Remember what we're jumping from and what we're jumping to. We're jumping from moles of NH3 to moles of H2. This is the mole-to-mole ratio, fraction number 3 here in our mass problem. So I bring down moles of NH3, and I'm going to jump to moles of H2. What is the ratio? Keep in mind, this is what we're jumping from. For every 2 moles of NH3, the 2 comes right there, comes from there. to, let's see, 3 moles of H2. It's a 3/2 in this case. Moles of NH3 gets canceled out. I apologize for the messiness. Last fraction, we need to jump from moles of H2, bring that down to grams of H2. So moles of H2 is on the bottom, grams of H2 is on the top. Once again, just like I mentioned a few minutes ago, the 3 here has already been taken care of with the mole to mole ratio. So when we're getting it back into grams, we're simply finding the molar mass of 1 mole. 1 mole of H2 will be whatever H2 is, 2.016. I think your periodic table has it as 1.008. Yep, so 2.016 is where that comes from. 2.016. I ran out of room, but we would hit the equals sign here, we'd pump the brakes, and we would do the math. Here we go, and then we'll be done. 43.2. Hopefully you can all see that. Divided by 17.04. I'm right here now. Times 3, because that's on top. Divided by 2, because that's on bottom. Times 2.016. And the answer for this particular problem to 3 sig figs is going to be rounded 7.67. 7.67 what? 7.67 grams of H2. Go back to the problem if you need the wording. And that is mass.